Good afternoon to all of you. Good afternoon, Namishka. I hope you all can hear me clearly and see my screen. Let's go ahead with today's class. Last lecture, we were talking about auditorium acoustics. We spoke about sound propagation outdoors. We talked about sound propagation indoors. And then we were talking about the lingering sound in a room, which is called reverberating sound or reverberation time. Today we are going to continue from that point onward. So, reverberant sound is the first topic that we will discuss. Air absorption, we have discussed and talked in our practical session, the sound absorbed by humans, objects, not by air. Air also does absorb some sound. So, we are going to talk about that. We are going to look at criteria for good acoustics. At the end, we will solve some of the problems. So please keep your pen paper ready so that you can note down some of the formulae and the problem solving. So reverberant sound, as we have already discussed, reverberant time is defined as time required for the sound pressure level to decay by 60 dB. So in Audacity, we have done that experiment. If you remember, if the sound pressure level is say 0 there, we have found reverberation time is the time that takes for the sound pressure level to drop to 60 or drop by 60 dB. So that we have already done. In a bare room where all the surfaces absorb the same fraction of sound offered to them. So in that case, the reverberation time is a constant into volume upon area. Now, remember, important criteria is here. You figure out the volume, figure out the area, calculate the reverberation time, but all the surfaces absorb the same fraction of the sound for this formula to apply. So if, that means all the surfaces must be similar or same. Derivation of this formula is out of the scope of our syllabus. It is called Sabine's formula of reverberation time, and it's a very exotic derivation. Earlier, earlier syllabus we used to talk and teach about the derivations, but in this syllabus we have skipped it. There are very few derivations in physics which are as exotic as the derivation of this formula. So if you are interested towards uh, mathematical physics or modeling physics, then do figure out the derivation of this formula. But we will take this formula as granted and go ahead. Larger rooms, you can see that if the volume increases, length, breadth, height increases, volume increase, area will increase. But remember, area is the product of two numbers, volume is the product of three numbers. So volume increases much faster than the area, and therefore larger rooms have larger reverberation time. That is important thing that we have learnt. In SI units, reverberation time is 0.161 into volume upon area, provided all the surfaces absorb the same fraction of sound. If the surfaces have different fractions of sound, then the formula gets little more challenging. Now here A is nothing but the actual surface area S into coefficient of absorption. Be careful. Coefficient of absorption does not have a unit. It is the ratio of amount of sound energy absorbed to the amount of sound energy incident. It does not have a unit. It is just a number between 0 and 1. 0 means no sound energy is absorbed. 1 means all the sound energy is absorbed. S into A will have the unit of meter square only. So this A will have the same unit of S, which is surface area, which is meter square. Although different surfaces area in a room can have different coefficient of absorptions, and therefore this formula gets modified depending upon the number of surface areas available. So A can be calculated if there are a number of such surfaces having surfaces area S1, S2, S3 dot 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 and having coefficient of absorptions A1, A2, A3 dot dot dot, then total A is S1, A1 plus S2, A2 plus S3, A3 plus dot dot. This is how you calculate your A. I suppose all of you are familiar. You have done this. If you have pen and paper around you, please write down this formula. We will need them for problem solving. RT is 0.161 V by A. A is equal to SA, and if there are number of such surfaces, then A is S1, A1 plus S2, A2 plus S3, A3, so on and so forth. Now the coefficient of absorption varies at frequencies. For human voice, you can take the figure of 125 male voice. You can take the frequency 125 for female voice. You can take 250. For other instruments, you can take these higher frequencies. There are different kind of materials which can be present in the room, and they have different coefficient of absorptions. I'm going to just look at, say, some frequency of around 500 hertz, and I'm going to focus on two materials which are least absorbing and most absorbing. So you can see that the least is 0.06, am I right? No, 0.02 terrazzo floor, some material. So 0.02 and 0.06, these are concrete and some sort of terrazzo, must be a kind of tiles. These are the special materials where the sound absorption is too little. So you can see that the hard surfaces, very hard surfaces, they don't absorb sound. Where the sound absorption is maximum. So 0.44 looks, here it is 0.93. So 0.93 acoustic tiles suspended. So you know acoustic tiles. Acoustic tiles are porous materials, and they can be suspended or they can be stuck on concrete. So if they are suspended, they absorb much more sound. If they are stuck on concrete, then their sound absorption is very little. So this is how the sound absorption varies. You can look at different frequencies and figure it out. So it depends, like what is the purpose of your room. If you're making a room for music, then you can look for these frequencies. The normal decay of sound energy is exponential. It decays this way with time. The log of this or sound pressure level decays linearly. However, not in all the rooms sound pressure level may decay linearly like this. There could be some variations. So it might be decay fast in beginning and decay slow later, or so on and so forth. Like if it's decaying exponentially in an ideal uniformly distributed sound, then this log or logarithmic scale is a straight line. But most of the time in large halls, theaters, auditoriums, the sound distribution is non-uniform. In a sense that in some corners sound will be too intense and some other corners sound may not be that intense. Therefore, as the sound decays, it travels from one side to other side, and therefore the non-linearity can come in. Sometimes the the room supports standing wave formation. Somebody has done some project calculation by which they had calculated the standing wave formation in a bathroom. So every room supports some standing wave formation, and those are the resonant formation at which the sound intensity increases. So at those frequencies you will get some higher intensities, otherwise it is dropping. So reverberant sound decays in different ways in different rooms. Now coming to the air absorption, sound is absorbed by air at high frequencies. Remember, air molecules are going to vibrate as the sound travels. And remember, the propagation of sound is an adiabatic process. That is, there is hardly enough time. It is not an isothermal process, it's an adiabatic process. There is no transfer, there is no time for heat transfer. Compression, the temperature increases. Rarefaction, temperature decreases. But what happens is that at high frequency, this small time becomes too little, and therefore, at some places, the molecules heat up and absorb the energy or heat up too much. And then, therefore, we can say that the energy is absorbed, energy is converted into thermal energy of air as the frequencies increase. It also depends on relative humidity. Typically, the formula, if you include that factor, then the formula looks this way. So earlier formula was 0.161 V by A. Now you introduce another coefficient into volume of the room. V is the volume. M is the coefficient. You can see that if you have to maintain the reverberation time at second, then this has to be dimensionless. Therefore, since V has the dimensions of meter cube, the M has to be a dimension of per meter cube. So basically, how much sound is absorbed by air is specified as per meter cube. Other sources of sound absorption are wood or metal seats, unoccupied, upholstered seats, unoccupied. Now, what are upholstered seats? The seats with cushions. So if you have a plain metal or wooden seat in a hall, unoccupied, then these are your coefficients. Remember, these are the coefficients per seat, not per unit area. I mean, you have to use it depending upon the number of seats. Here the unit is per meter square. Remember, these are not coefficient of absorption. These are coefficients, but coefficient of absorption was dimensionless. These have per meter square. So upholstered seats have different. So you can see that if you take bare wooden seat, coefficient of absorption is much less. But if you have upholstered seats, cushioned seats, the coefficient of absorption increases many-fold. Therefore, in a theater, you cannot, in an old styled theater where all the seats are, say, wooden, you remove the wooden seats and bring in cushioned seats. You cannot do that simply because the reverberation time will change, sound production will change. You will have to do something else to balance it. Upholstered seats with audience. So if people are sitting, then it will have even different absorption. So absorptions are going to be different. Air absorption finally, as I said, at lower frequencies, not very important, but higher frequencies, it's significant, and that has to be taken care into calculations. So all these things will come into calculation. So please be aware. Now, what are the criteria for good acoustics? This is a very important question. If you like music, listening music at your home, then you must know these ideas, and you must question that how good your home is for listening to music or speech or sound. So there has to be adequate loudness. Given the loudness is maintained by on the source, there should be adequate loudness in the room. Now remember, I'm going to talk about the small rooms in the next chapter. This chapter is actually about large rooms, halls, and auditoriums. In an auditorium, it may happen that if you're sitting closer to the source, the loudness may be high. But if you go away, loudness will drop. That should not happen if theater has to have a good acoustics. Adequate loudness must be maintained at all the places. The sound should be uniformly spread. There shouldn't be any dead spot. Dead spot means the the There shouldn't be any spot where no sound is there. Maybe because of a destructive interference, maybe because of a shadow, etc. No such spot should be there in an auditorium anywhere. Clarity. Remember, different instruments, different words, when are being spoken, they should be heard properly and deciphered properly by the audience. If it is not happening, that means there is a loss of clarity. Live, liveliness or reverberance. So music is said to be too dry, or speech both, they are said to be too dry if the reverberation time is very small. We need some sort of reverberation time for liveliness of the music. A long reverberation times will muddle the music once again. So one has to be careful. Echoes are very important. Remember, for you know how much minimum distance we need for the echo formation? You know that, right? 17 meter. Now you will realize that in any large theater, if you have gone for a movie, etc., then you know that the distance between the two walls can easily be more than 17 meters. 17 meters is not much distance. And therefore echoes would be created. Those echoes needs to be suppressed sufficiently so that the sound production is proper. Low background noise, outside noise. The theater must be shielded from the outside noise. There are various ways to do it. When we talk and discuss the noise topic later on, towards the end of this unit, then I'm going to talk about the noise shielding, etc. So low noise or low background noise is very important. Here are practical observations that what kind of reverberation time is needed for what kind of oral activities. You can see that the speech can go up till 0 to up to around zero point 0.8 second. But music typically starts with around 1 second and then can go up till higher value 1.2 second or 1.6 second, depending on what kind of music you are listening to. Different kind of music require different reverberation time. Music which plays, instruments which are played at a small interval, like you pluck it and just they give the sound. Example, a guitar wire, pluck it, it will give the sound. It does not require large reverberation time because it will be a lot of mixing of sound. But a flute, an instrument like a flute or like an organ pipe, which can play longer, can afford to be heard into a larger reverberation time. So 1.6 to 2 seconds, they appear to be more pleasant. On this graph, it's a room volume. So one can see that for larger room volumes, you require larger reverberation time for music to be or to appear nice. So idea is that there should be an optimum reverberation time. Too little reverberation time means the speech, audio, whatever is too dry to perceive, to experience. Too long reverberation time is again the sound will get mixed and muddled up. So there has to be an optimum reverberation time. The three things that we often look into are clarity, loudness, and liveliness or liveliness. Music typically needs longer reverberation time than speech, as we have taught. Different concert halls pose different uh, challenges. Smaller concert halls are they appear much more intimate. If you have a music system, good music system at your home or say in a theater, small theater nearby, and if you experience the music appears to be different. But if you go to a large theater, the music will be very, very different. So the challenge is in design, in acoustic design, the challenge is that how to mimic the experience of a small theater in a large auditorium at every place. Reverberation time or liveliness, as we said, spaciousness, apparent width of the theater, then surround sound. These days we talk about surround sound, how the listener is covered with sound from all directions, because our real life, the sound is surround sound. So if right now I'm sitting here, there is a road on one end from where the sound is coming, and some construction activity is happening at the other end of my building from where the sound is coming. Clarity, as we have already discussed, longer reverberation time would lead to the loss of clarity. Typical music requires different challenges: warmth, liveliness of the bass, balance, uh, left side, right side speakers, different balances, orchestra, the instruments kept on one side on the stage must balance with the musical instrument kept on the other side. It shouldn't happen that one side should be more powerful, overpowering than the other. Blend, mixing the sound from different instruments suitably is important. An ensemble, finally, in an orchestra, if you have seen, there are number of instruments are playing. Their ability to play together in harmony is important, and that's a job of the musician to create that ensemble. These are the world famous concert halls which who are made at different point of times, and these are their characteristics. Anyone doing any project, any ideas can use these. These are the volumes, floor areas. Volume wise, you can take a case study which is the highest in volume, 36,500. No, Royal Albert Hall, London, 86,600 meter cube. It has a reverberation time, and if you go ahead, you can see that 3.4 seconds, one of the highest here, 2.6 highest here, and 2.2 which is highest here too. In a good auditorium, you need to be careful. We need to avoid echoes, mostly by rear walls. Rear walls can most likely be happen to be at a distance 17 meter and beyond. So echoes may happen. So there are many ways to avoid it. You put absorbers, sound absorbers at the back wall so that not much sound is reflected. You make the back wall directional so that the sound is reflected in some other direction. Many ways to handle that situation. Flutter echoes, the reflections from the parallel wall. Typically, this problem comes in those auditoria which are narrow and long. So if the width is less, then the sound reflects from both sides and creates echo. That is called flutter echoes. That needs to be avoided again by putting suitable absorbers and reflectors on the side walls. Sound focusing, when you are putting so many sound reflectors at various places, it may happen by chance that at some point sound can get focused strongly, and at some point sound may not get focused that strong, and that creates an imbalance that needs to be taken care of. Unless and until it is intended, sound focusing needs to be avoided. Intended means, as I told you, If you go to Bijapur in Gol Gumbad, it's a monument. Stand in the gallery, whisper at one end, you will hear clearly at the other end. That's a whispering gallery. So there the sound focusing takes place. Sound shadows, as I have already talked about. Suppose if you have a broad pillar in the auditorium, you cannot avoid it using or during construction. Then the pillar actually creates a sound shadow, and that becomes a problem. Background noise, we have already discussed. We are going to talk more about this in the next chapter. So with this, we finish the theory part of this chapter. Let's check or let's take up some of the problems. Why does the use of cushioned seat helps to make the reverberation time of an auditorium independent of audience size? So the answer lies in the graph, the big this thing that I had shown here. You can see that if it is not cushioned, then the change in the time, the reverberation time is huge, tenfold, 0.014 to 0.13. But the corresponding change in upholstered seat unoccupied and audience in upholstered seat, the corresponding change is not much, 0.13, 0.27. Here the from unupholstered to upholstered, the sound reverberation time increases by 10 times. Here just double. Practically we can say that it remains the same. And therefore normally upholstered seats are preferred because when the because when normally when it is tested, audience are not sitting. When audiences are sitting there, then in that case it will not change by much. So that's a preferred. That's how the reverberation times of an auditorium becomes independent or roughly independent of audience size. What are the desirable reverberation time for speech and for orchestral music in an auditorium with 1000-meter cube volume? So let's go back to the different 1000-meter cube is here. You can see that for orchestral music, the reverberation time should be 1.7, 1.8 second. And you can see that it is not so good for speech production at all. So, like if you're music, then it's fine, but just for talking, it will not be that good theater. It will be mostly inadequate. Compare the absorption of 100 meters square of plastered wall with that of the 100 meters square of carpeted floor at 125 Hz and 2000 Hz. So that's a simple problem. We can take the meter square area, multiply by coefficient of absorption of plastered wall, figure out from the table, you already have the table, then multiply 100 meters square to the coefficient of absorption of carpeted floor. Again from the table, calculate for two frequencies, compare it. An auditorium has dimensions 40 meter, 20 meter and a ceiling height of 50 meters. So length is given, breadth is given, height is given. So volume you can calculate easily. If any one of you ready with pen and paper, you can calculate it. The front and back walls are covered with plywood paneling. So front and back walls. So now which will be a front wall and which will be a back wall, that you have to define. So 40 meter and 20 meter. You can assume that smaller walls are front and back walls. So plywood paneling coefficient you have to check. The floor is wood, so wooden coefficient. There are 1100 wooden seats. Remember, they are not cushioned. So you take the values for wooden seats, multiply by 1100, and then you use the formula 0.161 into V upon A plus MV. Figure it out when the hall is empty, half seats are filled, all the seats are occupied. So that's a easy doable problem. Estimate the time delay T1 of the first reflected sound from a person near the center of the auditorium described in exercise 2. Does the first reflection arrive from the side or from the overhead? So you draw the diagram and then figure out where does the first reflection will arrive. It all depends on distances and nothing challenging here. Find the reverberation time at 8,000 Hz for a very live room having a volume of 1000 meter cube when the temperature is 20 degrees Celsius and relative humidity is 30%. So you have to look at absorption by air. Absorption by wall is negligible, so you can ignore it. You can take coefficient of absorption as 0 and only so your formula 0.161 V by A plus MV, you can take A0 and calculate the reverberation time. You are looking at air absorption and then do it as your 10 power 3 meter cube. Look at the table. This has an interesting answer. So maybe we can stop here. We finished this chapter. Next chapter I'm going to talk about acoustics of small rooms. So thank you.